Hey everyone, and welcome to The Explainer. Let's just jump right in, because today we are tackling one of the absolute most fascinating and, let's be real, sometimes most frustrating parts of modern AI. We're popping the hood on diffusion-based text-to-image models. You know, those incredible tools that can synthesize ridiculously complex visual content from just a handful of words. But as we're going to see, figuring out exactly how that semantic structure emerges has been practically impossible to interpret, well, until now.
It's kind of the ultimate question, right? You spend all this time crafting the absolute perfect prompt, you hit generate, and boom. The AI just completely ignores a crucial detail. You ask for a red car, it gives you a blue one. You ask for a cat sitting on a table, and the cat is somehow floating in midair. So why does this happen? What is actually going wrong inside the model during those specific generation steps? Well, that is exactly the puzzle a team of researchers has recently solved, and that is exactly what we're unpacking today.
So here's our roadmap for today. We've got 1. The AI prompting black box. 2. Why aggregated data fails. 3. The visual analytics solution. 4. Tracking temporal and spatial shifts. 5. Enhancing human-AI collaboration. And 6. How to implement it.
All right, let's kick things off with Section 1, the AI prompting black box.
Right now, if you're doing prompt engineering or debugging, you're probably relying on what's called reactive inspection, which is basically just a fancy way of saying trial and error. It's totally a guessing game. If the model fails to render a specific object or totally misunderstands your prompt syntax, developers are largely forced to just blindly tweak the words, adjust a weight, cross their fingers, and hit generate again. You're inspecting the final image and reacting to it, rather than actually observing the generation process as it happens.
Moving right along to Section 2, why aggregated data fails.
So most workflows out there rely on aggregated summaries. Here's the thing. Standard inference pipelines actually do spit out attention tensors for every single denoising step. But most debugging tools take all that amazing, rich temporal data and just average it out. By tossing out the time dimension, you get this flattened trajectory that completely erases the sequence of events. But if we use step index tracking instead, we preserve the full temporal sequence, which totally unlocks the ability to have auto-segmented stages.
And this brilliantly illustrates why preserving that sequence is so absolutely critical. Think of generating an image like, building a house, right? Diffusion models definitely do not generate images linearly. First, they refine the coarse geometry. That's the early structural scaffolding. Then they move on to adding fine-grained details, the late texture synthesis. If you use an aggregated view that averages everything into a single frame, you completely erase the difference between pouring the foundation and painting the walls. A text token might dominate early on, fade in the middle, and re-emerge at the very end. Without step index tracking, developers simply can't verify if a prompt failure stems from an early misalignment, a mid-generation drift, or a total late-stage collapse.
Okay, Section 3, the visual analytics solution. As researchers Yuan Shao and George Lagradi point out, quote, the emergence and evolution of semantic structure remain difficult to interpret. And they hit the nail on the head there. Even though these models synthesize wildly complex things, we still struggle to see how they do it. Their work validates this exact frustration. So, to bridge this massive gap, they built a visual analytics framework specifically designed to map the step-indexed evolution of token-level cross-attention in diffusion models. They are literally opening up the black box.
So what is this framework actually tracking? Well, it completely ditches those static, flattened heat maps for interactive temporal and spatial views across 3 core dimensions. Number 1, step-indexed cross-attention map evolution. Number 2, temporal concentration shifts per token, meaning at what exact moment does a specific word in your prompt peak in its influence. And number 3, spatial relationships between competing tokens. Like, are 2 words in your prompt fighting for the exact same pixels? Instead of one messy summary, developers can finally watch exactly how attention mass migrates, stabilizes, or completely collapses across the entire denoising sequence.
Next up, Section 4, tracking temporal and spatial shifts.
Now, the researchers didn't just build this thing in a vacuum and hope for the best. The framework was rigorously validated through case studies on a structured 60-prompt Stable Diffusion class benchmark. And what they found was honestly pretty remarkable. By preserving that temporal dimension, the tool surfaced recurring, highly interpretable patterns in token behavior that the old static visualizations just completely and consistently miss.
Picture this. You've got a failing token. Let's say you asked for a golden retriever in your prompt, but the dog is just nowhere to be found in the final image.
With this framework, you can isolate that exact data point and ask a really targeted question. Did the failing token lose concentration prematurely? Did it actually just never gain spatial dominance to begin with? Or was it outcompeted by conflicting tokens in the prompt? This level of separation lets engineers pinpoint exactly when and where the semantic structure diverged from what they wanted.
Which brings us to Section 5, Enhancing Human-AI Collaboration. Here's the really crucial takeaway. Fixing a model gap doesn't always mean you need some massive, ridiculously expensive overhaul. Incorporating human semantic attention offers a super economic pathway to fixing errors. This is huge for safety-critical or grounding-heavy tasks where precise spatial alignment is a really big deal. Instead of burning time and money to retrain or fine-tune the whole model, developers can use this framework to intervene directly. You can observe the attention decay curves and manually inject corrective signals, adjust prompt weighting, or even modify the sampling schedules.
By linking those temporal and spatial views, teams can literally point to the exact step ranges where the attention just went off the rails. The interactive interface even lets you export quantitative measures for downstream analysis. Ultimately, this transforms prompt iteration and attention debugging from a total black box guessing game into a fully measurable, repeatable workflow. It's a real game changer.
And finally, Section 6, How to Implement It.
Honestly, the absolute best news about all this framework does not require any architectural changes to your diffusion model itself. It operates entirely as an external analytics layer that just ingests the standard cross-attention outputs your model is likely already producing anyway. No core model weight modifications are required. The whole shebang is highly accessible. So let's break down exactly how you build this out into 4 steps. Step 1, export your step-indexed cross-attention tensors during inference. Most modern implementations already compute these. You just got to ensure they're stored with token IDs, spatial coordinates, and step indices. Step 2, feed those tensors into the visual analytics interface. Quick pro tip here, if memory is tight, just prioritize the early and late generation phases where the really crucial structural decisions happen. Step 3, enable the stage identification module for auto-segmentation. That'll save you a ton of manual inspection time. And Step 4, cross-reference the spatial views with your prompt tokens. Isolate those failing tokens, track their decay curves, and adjust your weights or sampling steps as needed.
This is just such an incredible leap forward for human-AI collaboration. If you want to dive deeper into the benchmark configurations, the implementation notes, or all the nitty-gritty quantitative metrics, I highly encourage you to check out the archive preprint by Yiran Xiao and George Legrati. Which leaves us with one final kind of provocative question to ponder. With the black box finally opening and tools like this external analytics layer becoming available, will prompt engineering soon become a fully measurable science rather than just a guessing game? Thanks so much for hanging out with me for this explainer, and keep exploring.